In this video, I'm going to be doing a couple example problems involving cones and related rates. So in this example, we have a conical paper cup, and it's 30 centimeters tall. So imagine the snow cone cup that you get, or some athletes may recognize it as the type of cup you're given on the sidelines of a game. 30 centimeters tall, and it has a radius of 10 centimeters. So we have our dimensions here. Hopefully you can also recognize that we're going to be dealing with a right triangle somehow. The bottom of the cup is punctured so that the water level is going down at a rate of 4 centimeters per second. So what does that represent? It represents the height of the water. So this would be the rate at which the height is changing. And we want to find at what rate is the volume of the water in the cup changing when the water level is 2 centimeters. So let's figure out what information we have and what we need. Let's start off with the volume formula of a circular based cone. So the volume of a cone with a circular base is a third of pi r squared h. We also know the rate at which the height is changing, so we can call that dh dt, the rate at which the height is changing relative to time. And we're told that it's decreasing or going down, so we're going to give it a negative value. We want to find the rate at which the volume is changing, so we want to find dv of dt when the height of the water is 2, so when h is 2. So taking a look at our formula, we realize that we have two variables. We have an r and an h. Anytime I want to derive and work with related rates, I want to try and get my terms to be the same variable. So how could I replace either the r with an h or the h with an r here? So this is why working with cones is a little tricky. Try out this method. If I can establish similar triangles here, then I can actually solve for either r or h. So if I compare the radius to the height, so r to h, and then substitute what I know the radius is 10 and the height is 30. I can set up this proportion and I can cross multiply. So 30r equals 10h. That is the relationship of the radius compared to the height. And then I could solve for one of them. I'm going to solve for r. Just happens to make this problem a little bit easier. So if I divide both sides by 30 and reduce it, then r is equal to a third of h. So the radius relates to the height in that the radius is a third of the height in this specific cone. So now I can replace r with 1/3 h in my volume formula. And we're going to have to square that. So we can simplify a bit before we derive. So h squared times h is h cubed. On the bottom, I had 3 squared, which is 9. And then multiplying by that 3 over here in the other denominator gives me 9 times 3, which is 27. So simplifying, I now have 1/27 pi h cubed. And now I can derive this. So to find the derivative of the volume equation, that's how I maximize or minimize anything. Find the derivative. So the derivative of volume with respect to time is dv dt. 1/27 pi is a big constant term. We don't derive constants, so I'm going to shift that off to the side and just derive h cubed with respect to time. So I get 3h squared times dh dt. And now I can just substitute. We know that h is 2, so anywhere I see an h, I'm going to plug in a 2. I know that my change in height with respect to time was the rate -4 centimeters per second, so I can substitute -4 for dh dt and then simplify. So 2 squared is 4, times -4 is -16, times 3 is -48, times 1/27 means we're dividing by 27, times pi. And then we could actually find a decimal value and round to 3 decimal places, and it's approximately -5.585. So that is the rate at which the volume is changing at the exact moment when the water level is 2 centimeters in our cup. So we can say the volume is decreasing because we have a negative rate. At the approximate rate, 5.85 cubic centimeters per second. We're talking about a change in volume, so we're going to use cubic centimeters per second. at the exact moment when the height of the water level is 2 centimeters. Let's try one more example. This time the cup is 10 centimeters tall and it has a radius of 10 centimeters. The cup is being filled this time with water so that the water level, or H, is rising at this given rate. At what rate is water being poured into the cup when the water level is 4 centimeters? So first, let's interpret the information. Let's see what we have and what we need to solve for. Well, again, we're dealing with volume of a cone with a circular base. We're going to use the same volume formula. We are told the rate at which the water level is changing, or the rate at which H is changing. So dH dt is 2 over H, and it's rising, so we're going to make sure it's a positive rate of change. We want to find the rate at which water is being poured into the cup, so we can interpret that as the volume inside the cup is changing. So we're going to solve for the rate at which the volume is changing with respect to time at the exact moment when the water level is 4 centimeters, or when H is 4. So again, we got to make sure that we have a formula with variables that are all in the same term. So we got to substitute either R or H. So we're going to use that same technique where we compare the height to the radius and set up a proportion, cross multiply, and we're going to solve for R. When we do that, we get that R is the same as H. So this is a nice proportional cup where the radius is equal to the height. So now we can just substitute H for R into our volume formula and simplify a little bit. H squared times H is H cubed. Now we can find the derivative of our volume formula and differentiate each term with respect to t, or time. When we do that, the derivative of volume with respect to time is dv dt. 1/3 pi is a constant that we're just going to ignore, and we're going to differentiate H cubed with respect to time. So the derivative of H cubed with respect to time is 3H squared times dH dt. So what I did is I said if I'm multiplying by 3, that 3 that came to the front, and dividing by 3 here, that just goes away. So it simplifies to just pi times H squared times the derivative of H with respect to time. So now we can just substitute the values that we know. We know that H is going to be 4, so substitute 4 into the H spot. We know that the change in height with respect to time is 2 over whatever H is at this exact moment. So 2 over 4 is what we're going to substitute for dH dt. So I have 4 squared divided by 4, well, that's just 4. And 4 times 2 times pi is 8 pi. And then we could find the decimal equivalent, round to 3 decimal places, and get approximately 25.133. And now let's interpret our final solution. So water is being poured into this cup, and the volume is increasing because we have a positive rate of change at a rate of approximately 25.133 cubic centimeters every second at the time when the water level is exactly 4 centimeters. So there's some examples involving related rates and cones. Try and use that little method here where we can relate the height and the radius, and hopefully that'll help you figure out how we can do related rates with cones.